This is the third part of our lesson on rational function investigation. This is the third page on horizontal and oblique asymptotes. So it says, consider the following graphs and answer the questions below. So there are 6 different graphs that are here, and then there are some questions. So it says, looking at an equation of a rational function, how can you tell whether it's going to have a horizontal or an oblique asymptote? And I will, in a minute, encourage you to do this investigation on your own and then just check your answers with me. But first, we need to talk about horizontal and oblique asymptotes. So a horizontal asymptote is a horizontal line that your curve approaches but does not cross. So normally you might see it coming down and approaching like that, or it might be coming up from the bottom. An oblique asymptote, however, is a diagonal line that your curve is going to approach, right? So horizontal is flat, oblique is diagonal, it's on an angle. Okay, so when you look at your graphs, just to help you out, I would say this first one has a horizontal asymptote. I think that horizontal asymptote is at 0. If I look at this graph here, when I look at these two ends as they're heading off to infinity, I don't notice that they're leveling off on a horizontal line. I think they are actually following a diagonal line. So this one would have a horizontal asymptote, and this one would have an oblique asymptote. So when you're trying to find your asymptote, you want to look at the ends, right? As it goes to negative infinity, as it goes to positive infinity, where are those ends going? So I would recommend that you take a minute or two, try pausing the video, see now that you know what a horizontal and oblique asymptotes are, if you can figure out by looking at the equation when you're going to have a horizontal one and when you're going to have an oblique one. So take a second, pause your video, try the questions, and then check back and we'll take it up. Okay, so I am just quickly going to draw in the rest of the asymptotes. This one here, I notice the two ends seem to be leveling off around 1. So this one has a horizontal asymptote at 1. We already said this one was oblique. If I look at my two ends, this is approaching 0, this is approaching 0. So I'm confident in saying that this has a horizontal asymptote at 0. If I look at this one, this end is approaching, it looks like 2. This end is approaching 2. So I'm going to say there's a horizontal asymptote here at 2. And then on this one, this end is going to negative infinity. This end is going to positive infinity, which tells me that I think there is an oblique asymptote that this one is following. So of the graphs, A, B, D, and E all have horizontal asymptotes, and then C and D, these ones here on the end, have oblique asymptotes. So I guess the question is, what's different about the equations of A, B, D, and E compared to the equations for C and F? Well, this one here, they all seem to have one thing in their denominator, but these also have one thing in their denominator. And I don't know if you noticed, but these three all have the same denominator, x plus 2, x plus 2, x plus 2. And these three all have the same denominator, x minus 3, x minus 3, x minus 3. What's different are the numerators. So this one had a 1, this one had x, this one had x squared. This one here had a 2, this was 2x minus 5, and then this was 2x minus 5 times x minus 2. So on the first two, the numerator was a constant, so just a number. On the next two, the numerator had a degree of 1 or was linear. It's x and then 2x minus 5. And then the last one here, the degree here is 2. And if I were to multiply out this, x times x is x squared. So the degree of that one is also 2. So the ones that had oblique asymptotes had a degree of 2 in the numerator, whereas the other ones were a degree of 1, or I guess a degree of 0 if that's a constant. So will it always be that if it has a square in the numerator that it makes an oblique asymptote? No, that's not what it is. Really what's making it is the comparison between the denominator and the numerator, right? So here the denominator has a degree of 1. It has x to the power of 1. The numerator is a constant, so it has a degree of 0. So a degree of 1 is bigger than a degree of 0. Here, they have the same degree. I have x and x. They're both x to the power of 1. But here, I have x and then x squared. If I were to divide, does x go into 1? No, it doesn't have an x. It doesn't go in. It would go in 0 times. Oh, and look at this. My asymptote is at 0. What about this one? Does x divide into x? Yes, x would go into x 1 time. And where's my asymptote? At 1. Does x go into x squared? Yes, it does. You would have to multiply by x in order to make that happen. So because this goes in x and then it probably plus or minus something times, that's what's making the asymptote be on a diagonal. It has a slope. The other ones all had a slope of 0. If I check it with this one, does x divide into 2? No. So you'll notice this has an asymptote at 0. Does x go into 2x? Yes, it goes in 2 times. So you'll notice that my asymptote is at 2. And then this would be 2x squared. So how would I turn an x into a 2x squared? I'd have to multiply by 2x, which is why we're getting a diagonal. So how can you tell if it's going to be horizontal or oblique? You want to look at the numerator and the denominator. If the degree of the numerator is bigger than the degree of the denominator, it's going to be oblique. And if they're the same, or if it's smaller, then it's going to be horizontal, which is a little confusing. We're going to try to write it down in a way that we'll understand. So I'm going to say if the degree, that's the highest exponent, so if the degree of the numerator is bigger, I'm going to say than the degree of the denominator, but I don't want to write all that, so I'm going to say than the denominator, but I am talking about the degree. I'm going to say it will be oblique. And if not, it's horizontal. So when you have a rational expression, as long as you have, well, there has to be an x in the denominator for it to be a rational expression. So if there is a variable in the denominator, there will always be either a horizontal or an oblique asymptote. Now, vertical asymptotes, if you can't make it equal 0, there won't be any, but it doesn't matter. There will always be, as long as you have an x in the denominator, there will always be either a horizontal or an oblique asymptote in your function. So it says here, predict whether each of the following functions will have a horizontal asymptote or an oblique asymptote. So we're not interested in where it is. We're going to talk about that tomorrow. For now, we're just interested in how do I know whether it's horizontal or oblique. So if I take a look at the first one, m of x, I have 4x plus 1 divided by x. The numerator has x as its highest power. It would be x to the 1. The denominator is x to the power of 1. So they have the same degree. So the only time it's oblique is if the degree on top is bigger than the degree on the bottom. So since the degree here is the same, it's going to be horizontal. All right, what about the next one? The one here on top, the degree would be 2. That's my highest exponent. On the bottom, it's just an x, which is an x to the 1. So here, the degree is bigger on the top than the bottom, so that will make it oblique. And then the last one, the degree on the bottom has a power of 2. The degree on the top, well, it doesn't even have an x. It secretly has an x to the power of 0 if you want to write that in. So obviously it's bigger on the bottom. So it only is oblique if the degree on the top is bigger. So this one is horizontal. All right, so you're just looking, is the degree on the top bigger than the bottom? If yes, oblique. If no, horizontal. Okay, so the next page, the 4th page of the lesson, is practice. There are some good questions there to do that just practice finding vertical asymptotes, x-intercepts, and identifying whether it's going to have a horizontal or an oblique asymptote. All right, so try the practice and have a great day.